Welcome. In this video, we're going to discuss a game called Classic Nim. So this is really similar to Nim, except for one variation in the rules. So Classic Nim. We're going to start with the example of placing 9 counters as shown. Just like in regular Nim, the gameplay works exactly the same. You can take whatever you want from the first row, or whatever you want from the second row, or whatever you want from the third row on your turn. You can't take from 2 rows at the same time. So you can never take that one and that one, but you could take all of the middle row or this one and this one from the last row. This time, instead of making the last move of the game and winning, if you are forced to pick up the last counter and make the last move of the game, then you lose this game. So I want you to pause the video now. Try this game out, see if you can come up with any strategies, and we'll go through a solution to this game right away. All right, so how can we solve the 4-3-2 Classic Nim game? When I first was given this problem, my very first intuition was, well, for regular Nim, when we started with 4-3-2, that position was hot. So my first assumption was, well, maybe it's the opposite, and we actually have a cold position here. And maybe the game ends in the opposite winning condition, so we just have to swap hot and cold positions. Now, this couldn't be further from the truth. It turns out that after you think about this a bit more, Classic Nim has a winning strategy that's extremely similar to regular Nim. We just have to make an adjustment near the end of the game. So let's think about this state diagram below, and then we'll try to think about Nim sums with Classic Nim as well. So if you're playing at the very end of the game, and you are forced to pick up the last counter, you're playing from a cold position to a hot position. That would be a losing move. Now, every way that plays into the position 1 would become a hot position. So from 2, you could change it into a 1. From 2-1, you could take the 2. From 3-1, you could take the 3. And from 1-1, you could take one of the 1s. Okay, let's analyze 1-1-1. From there, there's 3 options, but they're all symmetric. And you have to take just one at a time. So you have to play into 1-1, which is a hot position, so that position has to be cold. So that immediately makes 3-1-1 hot and 2-1-1 hot. Now let's move over to 2-2. The 2-2 position, there's 2 choices from that. At least up to symmetry, there's 2 choices. You have to pick a row that has 2 in it, and you can either take 1 or 2. And both of those are hot positions. So that makes 2-2 a cold position. So 3-2, you can change the 3 into a 2, and 2-2-1, you can take the 1. They play into cold positions, so 3-2 and 2-2-1 are hot. Now, all 6 ways of playing from 3-2-1 are hot. 1, 2, 3, 4, 5, 6. Since that's all the ways of playing, giving you hot positions, 3-2-1 is a cold position, making 4-3-2 a hot position. So if you remember back from a previous video where we introduced the 4-3-2 Nim game, you're probably noticing a lot of similarities between hot and cold positions. In particular, this same starting move works for both Classic Nim and Nim. So again, it's the first player winning from 4-3-2. Okay, so for your interest, playing Nim under the rules of Classic Nim is called Messier play. So Messier is like the opposite winning condition, or the opposite counting. Sometimes we can think of Messier counting as like a game like golf. If you're playing golf, points are bad. In most games, you try to collect points and they're good. So let's see what kind of general analysis we can do for the game of Classic Nim. So as we were talking about before, the remark here summarizes that 4-3-2 Nim and Classic Nim are quite similar, same opening moves. So it turns out that the general winning strategy for classic NIM is also very similar to the general version of NIM. Now there's one definition that I'm going to use going forward just to make the language a little bit clearer. So in definition 3, we're going to define what we mean when we say big row. We're going to be pretty generous with the word big. It's going to become big as soon as we have more than one counter in a row. We're going to allow ourselves to call that a big row. So rows of size 2, 3, 4, everything above that are big rows. And the other rows that just have one counter in them, we're not allowed to call them big rows. So they're significant in the analysis of classic NIM. So that's why we're giving them a special name so that maybe every time we don't have to say this is a row that has more than one counter. Now we can just simply say big row. So in Theorem 2, we're going to suppose that classic NIM is going to start us off with 2 or more big rows. And when that happens, we have something really similar to the previous theorem. The game is in a hot position if and only if the NIM sum is non-zero. So there's this precondition of having some of the big rows to begin with. And it can't just be one big row. It has to be 2 or more big rows. So let's do a proof of this theorem. Let's see what that looks like. So the first player moves along so that the NIM sum is 0. And then the second player is forced to move, so it's non-zero. And they go back and forth like this. Eventually, because you're taking counters, we're going to run out of big rows, so there'll be less big rows because you continually take. At some point, there's going to be exactly one big row. Let's just draw a little picture off to the side to think about what that looks like. So we have a game of NIM, and it looks like one big row, so ... there's some counters there, and then in the other rows, there's just one counter in each of them. Let's say we have 4 rows, and it looks something like that. So which player would move so the game looks like this? Well, the first player is constantly moving so that the NIM sum is 0. If you have this situation, the NIM sum is not 0. Let's use S for the NIM sum like we were before. So S, that value is not 0 when the game looks like this. How do we know it's not 0? Well, a row of 1 cancels out with another row of 1. So you have 1 left over, or possibly you have an even number of rows that each have 1 counter in them. So the top part here is either worth 1 or 0 for the NIM sum, and that certainly won't cross out to give you 0 with that big row that's left over. So it's going to be the second player that does this. They move so that the NIM sum is non-zero and there's exactly one big row. Okay, so then at this point, we abandon the NIM sum. The first player says, forget about the NIM sum. Now I'm going to start thinking about the game with a different strategy. So from here, the first player takes counters from the big row, so operates on this big row, so that there's an odd number of rows left, each with 1 counter. So in our example above, if the first player was kind of counting this situation out, we'd say, okay, there's this last row, and we want to leave an odd number of counters left. So in that case, they would take the whole row. In another case, they might take the whole row except for 1. So at this point, if we draw a little diagram, the first player would move, so the game looks like that. And if we keep track of hot and cold, we'll kind of get a good idea of what's going on here, but let's keep going forward in the diagram before we do that. So what's going to happen is the second player is going to play next, and there's just a bunch of 1s left, rows with 1. So they're forced to pick up 1. And they will play back and forth in this way. The second player plays, and leaves just 2 counters. And because the second player is the one that's leaving an even amount of counters, it's going to be the second player that eventually takes the last counter and leaves an even amount of counters at 0. So, the game will end in a hot position with just 0 counters in this diagram that we're using. And then before that, the second player will have to play, from just 1 counter and play into that end game with 0 counters. So if we alternate back and forth, this position is hot, this position is hot, and the first player is excited to continually change those hot positions to cold positions, so there's nothing that the second player can do to win the game. And if we trace it all the way back to the beginning of our scenario here, this position here at the beginning is hot. And this one that comes after it is cold. Now, once again, the second player could steal this strategy if the game started with a 0 nim sum and at least 2 big rows. Let's go back to the diagram that we just looked at on the previous page, and let's try to analyze it with this theorem, just to try to solidify that a little bit more. So let's draw a line where we can find the place where there's just 1 big row. If we look closely, if we draw a dotted line here, here's my green dotted line, everything on this dotted line has just 1 big row. But all the positions above, if we count the number of big rows, there's more than 1. And everything below, of course, has 1 or possibly 0 big rows. So let's make a definition just for our diagram. Let's say B is the number of big rows, and S will be our nim sum. All right, time for a little activity. So everything above this green line, all of these positions, I want you to find the nim sum of all of those positions. And for every position above that line as well, let's write the B value. And for every position below it, we can realize that the B value is 1. So go ahead, pause the video now, and do that. Okay, so there's all of our nim sums indicated. So let's think how the first player goes through this game employing the winning strategy. So they start with a nim sum of 5, and they go ahead and take counters to change the nim sum to 0. The second player plays, and they have to play so that the nim sum is no longer 0. The first player plays and changes the nim sum back to 0. Thus far, this is exactly the same as regular nim. Now, as we go forward in the diagram, the second player makes their move, and the first player will have one of these options. This is where the first player changes their strategy. They change their outlook on the game. They no longer think about the nim sum. So that's why we didn't write any nim sums on these positions down here. They come up with a new strategy to play as soon as the B value is 1. And remember how we said it has to be the second player that changes the B value to 1. So from here on, we don't use the nim sum. Okay, but what should the first player do? What they do is they look at the big row and they make sure they leave an odd number of 1s left over. So either play into 3 1s or 1 1. And then the first player is guaranteed to win from that point on. It's the only choice for the game to play out. So let's look at some examples with a few more counters in other scenarios. Okay, so in the examples below, we're going to try to figure out who can always win, and if the first player can always win, we'll state the move that they need to make. Okay, so the first thing that we want to do in each situation is calculate the nim sum. So we calculate the nim sum, in this case it's 5, nim summed with 4, nim summed with 3. Okay, so to calculate that, we do 4 plus 1, in brackets, nim summed with 4, nim summed with 2 plus 1 in brackets. So cross out the 4s, there's 2 of those. Cross out the 1s, there's 2 of those. And there's a 2 left over. So s, this number, equals 2. So in the number s, we have to think about the largest power of 2 for the move that the first player has to make. The largest power of 2 is just 2 itself. Right? If we write that out as powers of 2, it's already a power of 2. So we have to then think, okay, which row contains 2 as one of the powers of 2 when you write out the sum of powers of 2? Well, the first row was 2 plus 1, so the first row contains it. The next row was 4, so that doesn't contain it. And the next row was 4 plus 1. So we have to pick the first row. So that's our first step. Calculate the nim sum, and then notice that our 2 to the power k is 2 to the power 1. And then in the second step, as we noticed, we'll pick row 1, because that's the one that has the 2 to the power 1 in it. So pick row 1. And then in our third step, we operate on row 1 by taking the amount that's in row 1, which is 3, and then we nim sum that with the nim sum itself, which is 2. So 3 nim summed with 2, 2 plus 1, nim summed with 2, cross out the 2's, and we're ending up with 1. That means that we want to make row 1, so this first row, we want to make that so it now just has 1 counter left. So our result, we want to take 2 from row 1. Okay, so that's our answer to this part. The first player can always win, and what they should do is take 2 from row 1, and it would look like, taking those 2. And let's notice that through all this work, everything that we've just done is exactly the same as regular nim. So the classic nim part of it didn't come into play here. It works the same. Let's move along to part B. So in part B, again, we're going to calculate our nim sum. So we have a nim sum to calculate of S1 nim summed with 1, nim summed with 5, nim summed with 5. We have a couple of repeated numbers that all cancel out, and we end up getting 0 as our nim sum. So in this case, the second player can always win. Let's look at one more example. Okay, so in this last example, if you're playing from this position, there is one big row. Obviously, there it is. So from this position, what you want to do is operate on that big row. So we don't use the nim sum when there's just exactly one big row. Now, what should we do? We should take everything from the big row to leave an odd number of counters left. So there's 1, 2, 3, 4, 5, 6 rows. What we want to do is take everything from the big row to leave 5 counters left, because 5 is an odd number. Okay, so the first player wipes all of those out, and that's our answer. First player is the winner here. The first player takes all of row 6. And if you wanted to just analyze it from here on out, it would be the second player, then the first player, then the second player, and then the first player, and then finally the second player would lose by taking that last counter. All right, so there's one more conclusion to our topic on nim. There are many variations of the game of nim. So here's one. It's called circle nim. So it's played on this circle below. So how do we play this one? We place a marker in each one of the circles below, and then players take turns, either removing 1 or 2 markers. But if they remove 2 markers, the 2 markers have to be beside each other with no empty circles between them. So if you're looking at the game board below, you could take these two at the same time, but you couldn't take those two. They have to be directly connected by one of these lines, and there can't be any empty removed ones between them. So you can take one, or you could take like these two, for example. So the player that removes the last marker is the winner. So this isn't classic circle nim. This is regular circle nim where you pick up the last one and you win. So try to think about a winning strategy. Let you pause the video now and see if you can come up with anything. Okay, so I'll go over a winning strategy to this game. So it turns out that the second player can always win, and what they can do is use a mirroring strategy. Or if that's the center of our circle, what the second player can do is constantly reflect the first player's move through the center. So let's say, for example, the first player decides to take this one right here. So if they go ahead and take that counter, then the second player will say, okay, I will just play on the opposite side of the circle and take that counter. And they will continue on playing in this way. And notice that there's a connection between one side of the circle and the other side of the circle. If the chip hasn't been taken here, then it hasn't been taken here. So that move of reflecting through the center will always be available to the second player. So let's say the first player says, okay, we'll take these two this time. So that one is gone and that one is gone. Now, the second player says, okay, we need to do that move and that move. So the second player responds by taking those counters off. And you can see that in this way, the second player will end up getting the last counter. So if the first player takes two, then the second player will take two. Or the first player could maybe take them one by one. If they do that, then the first player is still just not going to win the game because of that reflectional symmetry that we have going on here. So then the final one gets removed in the same way. So this is the second player picking up that very last counter and winning the game. So there's kind of a nice rotational symmetry that's going on here in this game. It doesn't matter how it's rotated to begin with. And I think that the game of Nim was thought of with some rotational symmetry as well. So we mentioned earlier that this is one of the oldest games in the world. Well, it wasn't solved until much later on in history. So it was solved. By solved, we mean we figured out the game of Nim in who can always win and what situations. So all of this Nim stuff, Nim sum stuff that we've been talking about. So it turns out that in 1901, a mathematician named Charles Boughton was the one that solved Nim. And Charles Boughton was the one that coined the name Nim, N-I-M. So I think that Charles was trying to be a little bit creative with rotational symmetry by writing the word Nim, because that word also has rotational symmetry. If we rotate the word Nim, we get another word that has to do with game theory, win. Okay, thanks so much for listening and checking out the video. We'll see you on the next one.